Today we are going to learn about interpreting SHAP values for feature importance. The goal is to understand how to apply SHAP values to see how features contribute to model predictions, enhancing transparency and interpretability. Welcome to our video on interpreting SHAP values for feature importance. SHAP, or Shapley Additive Explanations, is a game-theoretic approach used to explain the output of machine learning models. SHAP values are crucial because they provide a unified measure of feature importance, making model predictions more transparent. In this video, we'll explore how SHAP values not only enhance transparency but also offer advantages over other feature importance methods. By the end, you'll have a comprehensive understanding of how these values can improve the interpretability of your machine learning models. SHAP values are significant because they provide a unifying framework for interpreting machine learning models. Unlike other methods, SHAP is model-agnostic, meaning it can be applied to any machine learning model, from decision trees to neural networks. This versatility is one of its biggest strengths. SHAP values offer consistent and fair explanations by attributing the contribution of each feature to the model's prediction, using concepts from cooperative game theory. This ensures that each feature's contribution is considered in the context of all possible feature combinations, making it a fair representation. Another advantage of SHAP values is their ability to provide deep insight into feature contributions. For example, if you're working with a healthcare dataset, SHAP values can help determine which patient characteristics most significantly impact disease prediction. This level of insight can improve stakeholder trust, as the model's decisions become more understandable and transparent. SHAP values thus not only aid in model interpretability but also bridge the gap between data scientists and decision makers, enhancing collaboration and confidence in the model's outcomes. When discussing feature importance methods, it's essential to compare SHAP with other popular approaches such as LIME and permutation importance. LIME, or Local Interpretable Model-Agnostic Explanations, is similar to SHAP in being model-agnostic but differs in its approach. LIME approximates the model locally by fitting a simpler model around the prediction of interest. While useful, LIME can be less stable due to its dependency on the local approximation. SHAP, on the other hand, offers a consistency property, ensuring that if a model changes and the contribution of a feature increases, the SHAP value for that feature will not decrease. This consistency is a significant advantage, providing more reliable explanations. Permutation importance evaluates feature importance by measuring the decrease in model performance when a feature's values are randomly shuffled. Although this method is straightforward, it can be misleading, especially in datasets with correlated features. SHAP values account for feature interactions, providing a comprehensive analysis of how features contribute to predictions. This makes SHAP superior in offering a deeper understanding of feature contributions, ensuring more robust and interpretable model insights. Calculating SHAP values involves understanding the underlying concept of Shapley values from cooperative game theory. Shapley values represent a fair distribution of payouts to players based on their contribution to the total payout. In the context of machine learning, the players are the features, and the payout is the model's prediction. The calculation begins by evaluating the marginal contribution of each feature by considering all possible combinations of feature inputs. This involves computing the change in the expected model output when a feature is added to a subset of other features. In practice, calculating SHAP values can be computationally intensive due to the factorial number of possible combinations. However, the SHAP library in Python provides efficient algorithms to approximate these values, making it feasible for practical use. To implement SHAP values, you can use the SHAP library with a few lines of code. First, ensure you have your model and data ready. Then, import the SHAP library, create an explainer object for your model, and compute the SHAP values. A practical example would involve loading a dataset, training a model, and applying the SHAP explainer to compute and visualize SHAP values. This process not only demystifies the calculations but also showcases the practical application of SHAP values in real-world scenarios. Visualization plays a crucial role in interpreting SHAP values, transforming complex numerical data into understandable insights. There are several types of SHAP plots, each serving a distinct purpose. Summary plots are one of the most common visualizations, providing a high-level overview of feature importance across all instances in the dataset. These plots use color to represent feature values and show the impact of features on the prediction. Dependence plots, on the other hand, offer a deeper dive into individual feature effects. They plot SHAP values against feature values, highlighting how changes in a feature value influence the prediction. This is particularly useful for understanding nonlinear relationships and interactions between features. Additionally, Force plots provide an intuitive visualization of a single prediction, illustrating how each feature contributes to pushing the prediction from the base value to the observed value. These plots are interactive and allow users to explore specific predictions in detail. By leveraging these visualizations, you can enhance the interpretability of your model, making it easier to communicate insights to non-technical stakeholders and facilitate data-driven decision-making. Interpreting SHAP plots is an integral part of extracting insights from your model. Summary plots are particularly effective for analyzing the impact of multiple features simultaneously. By observing the spread of SHAP values for each feature, you can determine which features have the most significant influence on the model's predictions. This helps in identifying key drivers of the model's output. Feature interactions can be understood through dependence plots, which reveal how features interact with each other and affect the prediction. For instance, in a housing price prediction model, a dependence plot might show how the impact of number of bedrooms varies with house size. Such insights are crucial for understanding complex relationships within the data. Additionally, force plots help explain individual predictions by showing the contribution of each feature to the prediction. This level of detail is invaluable when you need to explain specific predictions to stakeholders or justify the model's decisions. By effectively interpreting these plots, you unlock a deeper understanding of your model, enabling more informed decisions and fostering trust in the model's outputs. Let's explore a real-world case study involving the application of SHAP values on a healthcare dataset. Suppose we're working with a dataset predicting the likelihood of heart disease based on various patient attributes such as age, cholesterol levels, blood pressure, and more. By applying SHAP values, we can identify which features are most significant in predicting heart disease. After training a model, we use SHAP to compute feature importance. Visualizing these SHAP values through summary and dependence plots allows us to see which features strongly influence the prediction. For instance, a summary plot might reveal that cholesterol levels and age are the most critical factors. Dependence plots can further show how high cholesterol levels sharply increase the risk prediction. This analysis not only provides insights into feature contributions but also improves model transparency by clearly showing stakeholders how decisions are made. The SHAP analysis helps healthcare professionals understand the model's reasoning, facilitating better patient care and more informed medical decisions. Through this case study, we see how SHAP values can be applied to real-world situations, offering actionable insights and enhancing the interpretability of machine learning models. While SHAP values offer a powerful tool for model interpretation, there are common pitfalls to be aware of. One key pitfall is misinterpreting SHAP values as causal indicators. SHAP values measure feature contribution, not causation, so it's important to avoid drawing causal conclusions without further analysis. Another pitfall involves ignoring feature correlations. SHAP values assume independence between features, which may not hold in real-world datasets with correlated features. This can lead to misleading interpretations, so it's crucial to consider feature interactions and dependencies. Over-relying on visualizations is another risk. While SHAP plots provide valuable insights, they should not replace deeper analysis. It's essential to supplement visual insights with domain knowledge and additional statistical analysis. Assumptions in SHAP calculations, such as the model's linearity or the dataset's distribution, can also affect interpretations. Being aware of these assumptions helps avoid overconfidence in the results. To ensure accurate interpretation, best practices include validating SHAP insights with domain expertise, considering feature interactions, and maintaining an awareness of the limitations and assumptions inherent in SHAP calculations. By being mindful of these pitfalls, you can leverage SHAP values effectively while avoiding common mistakes.
When using SHAP values in production environments, several best practices can enhance their effectiveness. Integrating SHAP into production involves setting up efficient computation strategies, as calculating SHAP values can be resource-intensive. Techniques like sampling and approximation can reduce computational load while maintaining accuracy. Ensuring model reliability is crucial in production settings. Regularly validate SHAP insights with updated datasets to confirm their consistency and reliability. This helps maintain trust in the model's outputs over time. Communicating insights to stakeholders is another key aspect. Use SHAP visualizations to present clear, interpretable insights, and supplement them with concise explanations tailored to the audience's understanding. This fosters better communication and collaboration between data scientists and decision makers. Continuous monitoring and evaluation of SHAP values and model performance are essential to ensure ongoing reliability. Regularly update the model and SHAP analysis to reflect changes in data patterns or business objectives. By following these best practices, you can effectively leverage SHAP values in production environments, ensuring that your models remain interpretable, reliable, and aligned with business goals.
In conclusion, SHAP values provide a powerful framework for interpreting machine learning models, enhancing transparency and insight into feature contributions. We've explored the significance of SHAP values, compared them with other methods, and discussed practical applications, including visualization and interpretation. By applying SHAP values, you can unlock valuable insights, improve model transparency, and foster trust among stakeholders. Remember to be mindful of common pitfalls and adhere to best practices when using SHAP in production environments. As you continue to learn and adapt, SHAP values will remain a vital tool in your data science toolkit, guiding you toward more interpretable and impactful machine learning models.